We're ending off this semester with this chapter about electrochemistry. So far what you've learned about electrons, hopefully in Chem 1 if you remember, but if not, it's okay, is that a lot of chemical reactions involve electrons being transferred, being shared, one of those two, and basically you'll get new bonds form usually. Or electrons will be transferred from one thing to another and it'll turn into an ion or something, right? So reactions like these. That's how you've learned the context of electrons and them transferring. In this chapter, we learn how the flow of electrons can be associated with electricity. Obviously, you know the importance of electricity for humans. And learning about this is important because it can lead to more efficient ways of generating electricity. For example, the fuel cell. It's basically a battery that is self-generating. Obviously, you know, there's still research required for this type of battery, but we will talk about that in a later video. First, we are going to review some Chem 1 topics. So the majority of this video specifically is a bunch of Chem 1 redox topics that we've learned about. But we visit them again because, you know, it's been a long time. And we actually need to visit them so in depth because, you know, it's the foundation for the rest of this chapter. Like all this terminology, you have to revisit it or else the rest of it won't make sense. So we're learning about redox reactions. So redox is short for oxidation and reduction. And these are reactions where you have electrons being transferred. So those examples I gave of, or I underlined of those different types of reactions, those are redox reactions. Yeah, we say redox for short. So atoms that lose electrons are being oxidized, while atoms that gain electrons are being reduced. So if you haven't heard the me for Chem 1, you know reduction is gaining, and that's in reference to Leo goes Gur, it's losing electrons is oxidation, gaining electrons is reduction. Here's this meme that I dug up on Google. Wow, the prices have been reduced, and then it's a price, and then electrons are being added, and now it's reduced. That pause was for you to laugh. Okay, so here are some examples. You're probably not laughing at all, you're just rolling your eyes, and that's okay. So here we have a full reaction, like a redox reaction, and then these are something called half reactions. These half reactions show you what's actually going on. So for oxidation, you start off with your element, and then, you know, our arrow symbolizes that the reaction occurred, and then at the end you have the ion and the electron because it lost it. So that's oxidation. Oxidation is losing, or losing electrons is oxidation. And then for reduction, we have the half reaction showing that we started off with our reactants with our element, and then we gained 2 electrons, right? And then, or we were going to gain the 2 electrons, and then the reaction happened, and then it actually gained the electrons. And now it's reduced. So definitely keep these acronyms in mind if you don't remember redox too clearly, and just kind of label it out for yourself. The best way to learn this is just to kind of make it very clear for yourself. It can get very confusing if you don't lay it out for yourself, like really in whatever way is organized for you in that way. So work on that first. Here is a slide that kind of outlines some tells for oxidation versus reduction. Now, something in here that we haven't discussed just yet, or we haven't discussed again just yet, or reviewed, is oxidation number. So we'll come back to that. But everything else we've kind of talked about a little bit. So when an element loses electrons, it's oxidation. When an element gains electrons, it's reduction. Something that you won't see in this class as often, but you will see like in organic. If you take organic and you learn about redox in there, if you see something gaining oxygen, it's oxidized. If you see something losing oxygen, it's reduced. So just, you can keep an eye out for that in that class. And then I talked about those half reactions, and we'll come back to this oxidation number stuff in a little bit. Here is another summary type slide. This one has some more terminology that you've learned in the past before. So, okay, yeah, we know the loss versus gain. You'll produce electrons, meaning you'll have electrons on the you'll have electrons on the product side, if they're produced. Sometimes I have to tell myself these things. For reduction, the electrons will be consumed, meaning they'll be on the reactant side. And in terms of how we kind of talk about this, whatever is reduced and whatever is oxidized, you'll say the species is oxidized versus the species is reduced. These reactions happen at the same exact time. You don't have like oxidation without reduction at the same time. The electrons have to come from somewhere and then they have to go somewhere, right? So this one, the whatever's oxidized loses it, whatever's reduced gains those same electrons. So you know how I just say how I just said whatever loses the electrons gives them up, and whatever is reduced gains them, right? So one thing has to give it up for the other. So something must cause the species to be reduced. So once you figure out, okay, A was oxidized, and we're going to talk about how you figure that out in a second, but let's say you figure out, okay, A was oxidized, and I have like A plus B gives me C and D, right? I said, okay, A is oxidized, B is reduced. By default, once you figure that out, and you know that's like fine, you can say A is the reducing agent, and B was the oxidizing agent. So whatever got oxidized is going to be the opposite agent, and whatever got reduced is going to be the opposite agent, right? So the oxidizing agent was reduced, as I said right here for B, and the reducing agent is oxidized, as I stated for A. Okay, so we're good with those terms. I know it's a lot of terms, but that's why we're reviewing them. Now we're going to review something called oxidation numbers. So this is something I kind of hinted at. We have to figure out how we actually determine what got reduced, what got oxidized. So how do we do that unless, obviously I tell you? There's a way you can do this with oxidation numbers. So these oxidation numbers are numbers that we assign, and they allow us to determine what got what got reduced. Oxidation numbers are they are another way, a different way of keeping track of electrons. So there's ionic charges, there's formal charges. Each of those we learn about in their own context. So ionic, we learn when we learn about ions. Formal charges we learn when we learned about Lewis structures. Oxidation numbers we learn with the topic about redox. Now, all of those numbers that I just mentioned, they all have to do with electrons. So you're probably like, okay, why is there so many different ways to keep track of electrons? Each of them have their own purpose. For oxidation numbers, it's to to be able to see what got oxidized, what got reduced. So we have rules that we can use to determine what the oxidation number of an element is. So we're going to go through those rules and we're going to practice. So I know that was a long explanation, but just to set that up for you. So yeah, there's rules that exist for assigning these oxidation numbers. So whenever something gets oxidized, this causes an increase in oxidation number. Anything more positive is an increase in oxidation number. So more positive is an increase in oxidation number, arrow. A reduction results in a decrease in oxidation number. Okay, so now let's go ahead and just practice. That's the best way this will work out if you just go right into it. So we're going to practice assigning oxidation numbers for each of these elements in the following compounds. Now remember I said there were some rules. I'm not going to go through the rules just because it's a bunch and it's just better if we just practice applying them. Hopefully it starts coming back to you. So that's what we're going to do. So first we have H2SO4. So the way that I do this is I kind of set up like this little, I don't know, train track type thing. And I figure out overall what the sum is going to be and then what the individual charges are that are contributed by each type of atom and how many of those atoms we have. So the first major rules is that an elemental form of elemental form of an element is going to be 0. This is when you only have one kind of atom. Some other major rules are that for a neutral compound, the sum of all the oxidation numbers is 0. So here we have a neutral compound. There's no charge on it, so the sum of all these oxidation numbers will have to be 0. For an ionic compound or a polyatomic ion, the sum of all the oxidation numbers should equal the charge. That's not the case for this, but for this one it's 0. After you figured these things out, like the easy stuff, those major rules, you go through each element specifically. So group 1A, +1 unless in elemental form. We have one of those here. We have hydrogen. And it has like its own specific rule, but it kind of usually applies to that as well. So it's +1 when bonded to a nonmetal, so when it's acting like its other counterparts of group 1A. We have 2 of them. So each one is +1, there's 2 of them. Overall, this is contributing like +2 to this overall charge right here. Next up, let's see, we don't have anything from group 2. We're done with hydrogen. So now we're at oxygen. Oxygen is -1 when in peroxides. In this case, it's not a peroxide. It's actually -2 as stated here in all other compounds. It's the most common. So we have 4 of them. Each one of them is -2, total -8. So now what we have is x left. So we have to solve for x. So +2 minus 8, in order for this to cancel out and equal 0, your x is going to equal +6. So the oxidation number for each of these elements, H, S, and 0, and oxygen, not 0, sorry. For hydrogen, it's +1. For sulfur, it's +6. And then for oxygen, it's -2. Right? Because we're looking at individual elements, not like their total contribution. So individually, these are the oxidation numbers. And you follow these rules like in order. So you saw how I was like going down the list and seeing what applied. That's how you typically use these. So let me clean this up and then we can move on to our next one. So our next one is a polyatomic ion, CO3. 2-, it's actually called carbonate. So Remember earlier I stated ionic compounds, the sum of their oxidation numbers will be whatever their charge is. So here we're going to set this up again. This is going to equal to -2. So you're always going to have a known and an unknown for determining oxidation numbers. The knowns are the ones that you're going to have directly on the rules. So for example, oxygen, we have -2 in all other compounds. This is not a peroxide. So we have 3 of them. Each of them is -2. So total, this contributes -6. So here we have x minus 6 equals -2. So to solve for that, x, if you solve for that, or when you solve for that, it's going to be +4. So the oxidation numbers for each of the individual atoms, for carbon, we figured out it's +4, that was our unknown. For oxygen, it's -2. So anytime something's not on this chart, that's your unknown, okay? Okay, so now we figured out, we have 2 so far done. That one. And finally, we have OF2. Okay, so we have oxygen, we have a neutral compound, and then fluorine right here. So I know, sorry, it's kind of hard to see, but for fluorine, it's -1 always. There's no exceptions. It's always -1. So we have, do we have any unknowns? We don't have any unknowns. So we know this is a neutral compound. Always start with that. And then go to each atom. So for sure, we know that fluorine is always -1. So we have 2. This is -2. In order for this to cancel out, oxygen has to be our unknown here. With fluorine, there's no exceptions. Like, it's very stubborn. It's just one of those weird situations. So in this case, our unknown is x for oxygen. And to cancel this out, it would have to be +2. So here, oxygen is +2. And then our fluorine, each one is -1 individually. So that's how you would determine oxidation numbers. I try to give you kind of like a variety of different ones with different unknowns. But, every situation is unique. So if you need to look up more videos on determining oxidation numbers, usually it's pretty simple, and we'll practice as we go along.